Ladies and gentlemen, welcome to the good afternoon and welcome to the WiFiMon share. First, let me introduce the team that we are working on WiFiMon. I'm here. My name is Kurt Baumann. I'm working at Switch and was at the project since the beginning of GÉANT 4.1. Nikos is working on the technical issues, especially on the streaming logs, correlation approaches, user interface, and also on the software-hardware probes. Sokol is working on the streaming logs and correlations. He was building the ELK cluster and was also involved in the main cluster in building the infrastructure on Switch engines. Kostas is acting, I think, for me, the advisory role. He's working on all topics and is supporting Nikos and Sokol on technical issues. And Sotne, I would say he is the member to the NMAS team. He is working with us on Dockerization of WiFiMon, and Pavle is the task leader of this group. Next slide, please. So, and we like to introduce now the project. We'll give you an overview in the next 45 minutes about the technical approaches, how it works, about the log streams correlation and the cluster that Sokol and Nikos has built. And at the end, I would say the demo on the measurements, that we give you some impressions about different proof of concept that we have tested, and we got some results from them. Next slide, please. So the big question was, why a system? Why a system for Wi-Fi monitoring? And as you know, the Wi-Fi is called the last mile, so the uplink to the internet, and it's still the fastest connection that we can have at the moment on the campus in a wireless approach. The consequence of that is that the Wi-Fi comes up to the most popular network. It's also most challenging to measure the performance also on the campus, and this has some reasons, because wireless is sharing the air, sharing the spectrum. We have some physical obstacles, means constraints, and we have also interferences from other networks, and of course we have some signal reflections and diffractions. These are only one statements that we are cope with in wireless. So, however, we conclude in our expertise that the signal strength and the link quality on fixed location is nice, but to have it is nice, but it's not everything, right? So what we need is the impression of the end user. We are calling this the experience, the quality of experience, and this is what we present. What we like to present to you. And furthermore, if you take a look about the vendor solutions, and then it's more or less, yeah, it's closed. You have less freedom for further deployments, for extensions, and also system improvements. Next slide, please. What is WiFiMon offering to you? So, as I said, so the WiFiMon tool, or mentioned a little bit, the WiFiMon tool is a vendor independent. It's an open source tool. We have also open source testing tools from Akamai Boomerang and Speedtest in place. It's transparent to the end user, and it's working non-invasive in this case. We have less overhead on the spectrum, and what is important is we capture users' perception of the network quality. also providing some metrics, so throughput, latency, signal strength, and link quality. And we build upon this open source approach with open source tools that we are using ELK, we are using the Akamai Boomerang that I mentioned, and also Speedtest. So next slide, please. So some brief history. As we started with WiFiMon, this was in GÉANT 4.1, we started with the question, is it possible to gather data from multiple sources, including browser-based measurements, in addition to traditional monitoring, and extract meaningful information on the performance of a Wi-Fi network from that data? And today I can say, yes, it's possible. And we have, and we like to present this today in this 45 minutes, how we have, what is the solution approach for that. Please, next slide. So here you see the building blocks that you have in place. So we have the client, this is you and me. We have some sites on the campus, WiFiMon enabled. We have the WiFiMon test server where the templates are running, and the location are defined where the templates are running. We have the wireless access analysis server where we analyze the data, where we analyze the data and storing the data and visualize it. And please, next one. This is a short walkthrough to this system. The client is visit some site on the campus. Next one. He is downloading the JavaScript that will running the throughput and the latency behind. The tests will be fetched to the wireless test server, and results will be analyzed on the wireless analysis server. Please, next one. So from this scope, we decided what could be the scope of a service model. And we listed two specific opportunities. The first one is you install on your campus, the WiFiMon is an installation, all the campus, all the components on your premise. Then the second one, if you would like to try to test, then you get from the WiFiMon team wireless analysis server on an instance on the NMAS. It's Dockerized, and this allows you to test, to get some first step and experience. With the option one, you have a clear statement that it's running on your campus. There is no personal data sharing with third-party organizations. And whenever you are interested in WiFiMon, you have here the link, and you are very welcome to share with us your interests and your ideas. Next slide, please. So these are the references we have now, and the WiFiMon page, the code that you can download it, the software, and publications and more impressions about WiFiMon. And now, if I understand it correctly, we are coming to Nikos, and Nikos will tell you more detailed technical approaches of WiFiMon. Thank you.
Yeah, thank you, Kurt. Just to mention that you can download this presentation. It is on the events page of where you registered, GÉANT's events page, and this presentation with all these links is over there. So I will now stop sharing, and Nikos, give the floor to you.
Hello, everyone. Can you see my PDF?
Yep.
Yes.
Okay. Hello, then. I'm Nikos, and I will present you more technical details about the components that WiFiMon uses and its technology. First, I will start with a figure that presents the overall architecture of WiFiMon. As you may see, there is a WiFiMon administrator who performs some edits in a component that is called the WiFiMon analysis server. The WiFiMon analysis server is the main component that analyzes performance measurements or other sources of data and provides visualization to the administrator. So the first thing that the administrator has to do is to configure the subnets that are going to be monitored. As you may see on the figure, WiFiMon has two sources of data. There may be performance data sources and accounting data sources. In the first case, performance data sources, we can have two types of measurements, as Kurt said earlier. We can have measurements from software probes, which are end user devices, such as Wi-Fi enabled devices, a mobile phone, a laptop, or you can have deterministic measurements from devices called hardware probes. These are devices that monitor the Wi-Fi network from fixed points. In WiFiMon, we have used particularly Raspberry Pis to do this job, but any other device that that level could be used. The second source of data are the WiFiMon accounting data. These are data exported from the radius or the DHCP server that serves the software or hardware probes. And the radius logs and DHCP logs are exported from the servers using a FileBit agent. As you may see on the figure, the FileBit agent exports these logs and delivers them to the WiFiMon analysis server to be further processed. And now we are coming to the process of how a measurement works. Kurt earlier described with shorter what happens, but let me tell you again. First, either a software probe or hardware probe visits a monitored website. A monitored website is a website in which we have injected some JavaScript lines directing to the WiFiMon test server. The purpose of the test server, this component, the purpose of the test server is to hold the test tools used by WiFiMon to measure performance. So a probe visits the monitored website, brings the HTML code back with JavaScript lines, and automatically starts the performance tests. It downloads some test data. This could be garbage data or images, small images, and calculates performance results. These results are then streamed to the WiFiMon analysis server. Now let's go further into the installation instructions of the WiFiMon test server. As I said before, this component holds the images and code required for WiFiMon measurements. And the main steps to install it are simple. You just install an Apache web server. WiFiMon currently uses Apache, but I think we could try in the future with other web servers. You have to enable cross-origin resource sharing. And you have to include the JavaScript code of the 3 test tools. We're currently using 3 test tools. These are the net test, which is a rather older test tool, but we are still using it to gain some insight. But the most important tools are Boomerang, which is developed by Akamai, and Speedtest, which is developed by Libretest. This is the name of the repository. It is not the O-class Speedtest that you perform in your browser. And this is the main technology behind the. As you can see, this is a monitored website. You just have to go and include these lines that point to the WiFiMon test server. And once the probe, either software or hardware probe, visits this website, the measurements will be triggered in an automatic manner. And as you can see, there are some important attributes. For example, the IP of the WiFiMon analysis server, the location of the images, and the cookie that I will explain later. What is very important here is that there is an attribute that specifies that the measurements will be triggered after the page has loaded in the device of the end user, and thus the experience of the end user is not impacted. Now let's go to the Wi-Fi hardware probes. These are, recall that these are tests from fixed points in the network that can be used to verify the accuracy of the crowdsourced tests. As I said before, we're currently using Raspberry Pi 3 models, but later we can, of course, obtain the fourth version of Raspberry Pis and test the 5 gigahertz band information. The image is, you can install the hardware probes in two ways. Either include the required code to an already installed Raspberry Pi operating system, which is rather easy. It is two scripts, and or you can get a pre-configured image from us and just edit the parameters. Okay. These are the installation steps for the probes. What you have to do is write for our pre-configured WiFiMon image. You write the image to the micro SD card, you connect to the network you want to measure, and you configure the test tools and how often, which test tools and how often they are triggered by editing a cron tab. And last, you have a Python script that is that obtains wireless network metrics and streams them to the WiFiMon analysis server for processing. What are these metrics? These metrics may involve the access point that the probe is connected to, the ESSID that's associated with the probe, the link quality, bitrate, signal level, and transmission power of the wireless network card. And these are information that you obtain regarding the hardware probe. You can also obtain important information about the surroundings of the hardware probe in order to check what is the reason for lower network quality. And this could be the MAC address of the nearby access points, their associated ESSID, and the signal level and link quality of them. In the future, we will also include the channel encryption. It is rather easy. It is a few lines of code. It is just something that we did recently. And now let's delve deeper into the last component, the WiFi analysis station. Recall that the administrator edits, inserts the subnets that will be monitored by WiFiMon, and these configurations of the administrator are stored in a Postgres database. You can see that the Wi-Fi analysis server receives two kinds of data, as we said before, performance and accounting data. And for the performance data, there is a WiFiMon agent, one of the components, one of the functionalities of the Wi-Fi analysis station that processes these measurements, correlates them with available radius or DHCP logs, and stores the results in the Elasticsearch cluster. Regarding the accounting data, radius and DHCP logs, we have a Logstash instance that that stands before Elasticsearch, which is used to anonymize sensitive information, such as the MAC address of the end user device and the IP address of the end user device. And finally, we provide dashboards in order for the administrator to visualize the results. And the analysis station, to install the analysis station, you just install PostgreSQL, configure databases, etc., install Java, install and configure the ELK cluster, use the Java code for the WiFiMon agent and the WiFiMon UI, create indices in Elasticsearch or import pre-configured dashboards, and optionally, but important, you can configure the WiFiMon secure agent, which is with the Wi-Fi analysis station working over HTTPS. You can correlate with radius and DHCP logs. This is a good point to say that WiFiMon is independent of the Wi-Fi technology. You can use WiFiMon for any Wi-Fi network, but you will get the additional benefits of correlation with radius and DHCP logs in IEEE 801.x networks. And finally, you can configure XPack in order to provide TLS encryption and security in the Elasticsearch cluster. Okay, this is rather complicated, but what is important here is that there are two main optimizations in WiFiMon in order to avoid to overload the Wi-Fi analysis server. The first one is the register subnets. I already told you before that the administrator defines the subnets that will be monitored. Why this happens? Because when you inject the JavaScript lines to a famous, let's say a popular visited website, such as in a campus network, you expect that users from the Wi-Fi network that is monitored will visit this website, but also users outside the network. So this is a method to drop the measurements that come from outside the monitored Wi-Fi network. And we have a cookie. The cookie is that repeated measurements in short time intervals are not permitted. The default cookie is 1.5 minutes, but it can set lower or higher. And finally, this describes the process of correlating with radius and DHCP logs. The main idea is that when you get a performance measurement, you also get the IP of the end user. So you're searching in radius log to see what's the last connection for this IP address and correlate the end user measurements with the access point in the networks. Otherwise, you cannot get information from crowdsourced measurements for access points. DHCP logs are used because the IP address of the end user in the radius logs is not always available, and thus we use the DHCP address to the DHCP server to find the MAC address corresponding to this IP address and correlate based on the IP address, because the MAC address is commonly available in the radius logs. And I think, okay, this is the end. So call.
Hello. Can you see the slides?
Yes.
Yes.
Okay. So my name is Sokol Jesi, and I've been working about the streaming of logs in the ELK cluster, configuring the cluster, setting up the components, and so on. So what I will present is about some details for the cluster itself. We see here in this image the main components, the main consists of the cluster, which is the file bit, which is installed in the Radius and DHCP servers to consume logs from those services. Logs are going over the TLS encryption in the log stash. Here happens the anonymation. There is hashing functions which are applied to some sensitive fields. So we are conform with the GDPR instructions. And finally, those data are enriched and are manipulated according to the needs of the WiFiMon and are forwarded in the cluster itself, again over the TLS encryption channels. So here what we see is a bit deeper what happens in the file bits. In the left side, it's about some configuration lines in the file bits. In the Radius server, those 3 lines is how Radius log event is calculated. And in the right side is the DHCP lines, which is just a line which includes lines from logs that have the DHCP acknowledge, which is the final phase of the DHCP operation. This holds all the information we need about the correlation with user measurement data. The bottom part is a field named log type, which we add, and this field holds the radius or the DHCP value, and this makes it possible to separate the streams when they reach the Logstash service. And here is what happens in the Logstash. We have 3 pipelines. The first one is the bit pipeline. Each pipeline has 3 items, 3 elements. It's about the input, the output, and the filter one. The first one, the bits pipeline, doesn't configure any filter pipeline. It just receives data and forwards. It's a kind of routing pipeline, and it serves for the others two pipeline. It configures the Logstash as to listen for events. It configures a port there, and configures also the TLS communication encryption. The Logstash acts as a server and as a client because it is receiving and forwarding data as well. So in the 2 pipelines, in other 2 pipelines, we see a list of the fields we collect from the respective logs. So for example, in the radius pipeline, we see calling station ID, framed IP address when this exists, and some other fields. Some fields, the first one, the first 2 in each pipelines are hashed. This is the anonymization of those fields, and both those fields make references in the ILM policy, because these fields that this data that we extract from logs are not needed. There's no need to be there for a long time. We delete them when after 1 day, when they are 1 day old, we delete them. And the last action is the output of those pipelines, which send that data in the radius logs and DHCP logs. These are indexed in the Elasticsearch cluster. And our Elasticsearch cluster consists of 3 master eligible data nodes and another one which is the coordinating node. Master eligible means that these nodes can be elected as master, because every cluster has a master node which coordinates the control the works in the other nodes of the cluster. But they are also data nodes. They can hold data, can apply operation on those data, and so on. There is another coordinating node. This is a cluster node, Elasticsearch node, but it doesn't hold any data. It cannot be elected as a master node in the cluster. It has no functionalities, and so being without those functionality, in fact, it acts as a load balancer node. Those cluster has the XPack security for the HTTP and transport. HTTP is those are different to the 2 main protocols of the Elasticsearch, which are used for the data, for the nodes to communicate with each other, to transport data and queries and monitoring data. Kibana platform is also installed in the coordinating node. The cluster has, the Elasticsearch cluster comes with some built-in users, and we set up those users' password in order for these users to be able to authenticate. As I mentioned before, there is the ILM policy to delete the radius logs and the DHCP logs indexes when they are old. And we also make use of key store to store sensitive data. Each Elasticsearch component comes with a key store implementation, and we can hold their user password, certificate keys, passphrases, and whatever we consider sensitive. And this sensitive data can be referenced from the configuration files. So we don't have sensitive data hard-coded in the configuration files. This adds a layer to the security in general. And at this point, our cluster, our current version cluster is what I explained just before. And the Logstash and coordinating nodes are single point of failures. We are working on the next version, and our next version cluster will add 2 nodes, one for each SPOF functionality, so we will eliminate those single point of failures. We use legacy methods for monitoring because when we started the cluster version, there was not the metric bit collection method of monitoring data. It was released some minor releases, Elasticsearch releases, after we started. So we plan to update to this new method, which is the recommended one from the Elasticsearch. And we will also, our next version will have a separated cluster for dedicated to the monitoring of the main cluster, of the production cluster. And this has 2 benefits. The one is that the monitoring functionality or performance or traffic of data doesn't impact the main cluster. And whatever happens in the main cluster, if for whatever reason it goes down and is not accessible, you have the monitoring cluster, so you have the monitoring data. So it is better to have those 2 clusters separated. And all this configuration setup that consists the ELK cluster, we want this to be, it is documented, the first one, the first version. For the new version we are working, and so we don't have at this moment the documentation, but we want this new version to be automated, and we are working it directly in the Ansible, and it will be provided as an Ansible collection of rules for each components in order to run these playbooks and have the cluster set up and configured. So this is from me. Thank you very much. And Nikos, it goes for you.
Thank you, Zoko.
Hello again. Okay. Oops. You can see my screen, right?
Yes.
Okay, in this part of the presentation, we're going to show you some results from our recent pilots. We ran 2 pilots in the past. The first was in the TNC19 in Berlin. The other was in the GÉANT Symposium in Ljubljana. And the part will end with a pre-recorded demo demonstrating all the parts of WiFiMon. Okay, this is an image from our pilot in TNC19. In this conference, we mainly tested our hardware probes. As you can see, we used 5 hardware probes, and we used the laptops of our teams. Unfortunately, we were a bit late to include a privacy notice in the conference page, and we didn't get any crowdsourced measurements. But still, we got some very important conclusions. As you can see, the WiFiMon test server was located in Taltech in Tallinn. It was not located in the network that was monitored, and the WiFiMon analysis server was located at Switch. It was a VM at Switch. One important thing that I forgot earlier is that the placement of the WiFiMon analysis server is not important. It can be anywhere. It's just a VM that analyzes the results. However, the placement of the WiFiMon test server is extremely important, because when you download this test pages, the round trip time between the end user and the WiFiMon test server is included in the measurements. So the perfect setup is to include the WiFiMon test server in the network that is monitored. But also, if you have something very close, it is okay. Here, the RTT was about 2 milliseconds or less. It was small. And this is an image mainly from the main room that included the lightning talks. As you can see, we started monitoring at 2 p.m. and the figure ends at 9 p.m. We had the only one probe there in the room, and as you can see, there were some problems between 2 p.m. and 3:30. These problems could be low. We also had low throughput, but we also got some disconnections from the hardware probes. Later, after the lightning talks ended, the people went to eat in a nearby room, and as you can see, the performance of the Wi-Fi network is better. Later, people returned for an opening reception that took place extremely close to this room, and as you can see, the performance of the Wi-Fi is worse. And later, as people left for the night, the performance is okay again. So we can see that the WiFiMon is able to capture performance, Wi-Fi performance degradations. In the first part, you have the lightning talk, which had a lot of people there in the room. The second part was people left for noon, for afternoon, and they returned for the open reception at 5 p.m. Now let's go to the second pilot. The second pilot was in the GÉANT Symposium in Ljubljana. This time we were able to also have crowdsourced measurements. In this case, we added the JavaScript lines in the Symposium agenda. Apart from the agenda, there was also an app that monitored where users could go and see the program of the Symposium. Unfortunately, we were not very aware of this, and we didn't include any JavaScript lines there. But WiFiMon also includes an app that could be used in this manner. And for the deterministic measurements, we had 7 hardware probes with a measurement interval of 5 minutes. Every 5 minutes, the probe performed a measurement. And this is the results that we got from a hardware probe included in the Grand Foyer. The Grand Foyer was the room that people met to drink their coffee, to have lunch, etc., etc. And as you can also, it was extremely close to the main room where there was the opening plenary and the evening plenary. As you can see, also in this case, we are able to detect performance degradation. In the first part, between 9 and 10:15, it is the opening plenary, and you see that a lot of people are there, and the performance degrades minor degradation. Then you can see that the second degradation is during the coffee break, which is after 2:30 p.m. This is a serious performance degradation. A lot of people were there to eat and drink. And then they go to their sessions. The performance is okay again after 4 p.m. But later in the evening, that they meet after the evening plenary, that people meet to chat, we see again degradation. These are the results from monitoring the main hall. The main hall was the room that the main sessions took place. You can see that also in this case, you were able to detect the degradation, and that both probes follow the same pattern. The probes were placed at the 2 sides of the room, the one on the one side and the other on the other extreme. And you can see that the results are similar. Of course, not identical, but similar. And these are the crowdsourced measurements. If you compare them with the previous slide, I should have used them together. Sorry. You can see that the crowdsourced measurements, the measurements obtained from the end users, follow the same patterns as the deterministic ones. Sorry, this is all these figures are for the average download throughput calculated, the time required for the probes to download the test pages. WiFiMon can also measure the upload throughput by uploading very small images or test data, and it can also measure an HTTP ping, not an ICMP ping in the way we're accustomed to that, but an HTTP ping, the route trip time. And these are the wireless metrics that I mentioned before. Recall that apart from performing measurements towards the WiFiMon test server, the hardware probes also collect some metrics and stream them to the WiFiMon analysis server. These metrics can be signal level, bitrate, link quality, transmission power, and you can see all the measurements from the 7 probes, and they're measured in an average, of course, download throughput, upload throughput, and ping latency, HTTP ping. You can see that the throughput measurements do not necessarily follow the trends of the wireless metrics. For example, you can observe the first line, that is the hardware probe 1. You can see that it has the best link quality, 60, but the throughput measurements are lower than other hardware probes. Also, in the 5th line, the hardware probe 5, you can see that the link quality is less than the other probes, but the throughputs are better. So this is an important conclusion that deterministic measurements alone cannot reach essential conclusions about the Wi-Fi performance. We also need the crowdsourced measurements. Okay, and now the WiFiMon demo. In the WiFiMon demo, it is about 5 minutes. You will see the WiFiMon user interface. I'm going to edit the subnet tab. Recall that there is you have to give the network that is going to be monitored, in order to avoid overloading the WiFiMon analysis server with measurements that originate from outside the monitored network. Then we are going to trigger a WiFiMon measurement against the WiFiMon test server. You will see that the results are a bit are not very good, but please bear in mind that this test server is located at Switch in Lausanne, and I am performing the measurements from Athens. Recall that the WiFiMon test server should be located close to you. You will also see the dashboards, both Kibana dashboards and that are visible from the user interface. Correlation with radius logs, not DCP logs, but it doesn't matter a lot. And metrics from probes. Pavle, you will play the video. Okay, thanks. Hello everyone, I'm going to show you the basics behind using WiFiMon. Although WiFiMon is used to monitor wireless networks, for the purpose of this demo, I'm going to show you measurements over a wired network. The first thing I'm going to do is to log in the WiFiMon user interface. Once I log in, I get the Overview tab, which includes a summarization of all the measurements performed by WiFiMon. As you can see, during the last day, WiFiMon has processed 87 total measurements. Now, if I want to measure the performance of a wireless network, the first thing I'm going to do is to go to the Configuration tab, Subnets, and include the side notation of the subnet I'm going to monitor. Now I'm ready to perform a measurement. This is the website I'm going to visit in order to trigger a measurement against the WiFiMon test server. The test tool I'm going to use is the Speedtest tool. This website has been embedded with the required JavaScript lines to trigger the WiFiMon measurements. Here in the console, you can see the information that is exchanged when I visit this website. First, the WiFiMon analysis server verifies that the subnet of the end user is included in the monitored subnets by WiFiMon. Afterwards, the end user downloads test data in order to calculate performance results and stream them later in the WiFiMon analysis server. But while we're waiting for the test to finish, let me show you a sample Radius log. This is a Radius log as exported by the FileBit instance installed on the Radius server. Important information to see here is that the called station ID, this is the MAC address of the end user device, and the framed IP address, this is the IP address of the end user device, are plain text. However, if you visit the Kibana user interface installed on the WiFiMon analysis server and see what is stored for Radius logs, you can see that this sensitive information is stored anonymized in the Elasticsearch cluster. This is because the log stash that resides in front of the Elasticsearch cluster anonymizes this data when it receives them. Now, the end user measurement we triggered before is probably over. Let me show you what is stored in the Elasticsearch cluster in the WiFiMon index. This is the measurement we triggered before, and as you can see, it includes information correlated with Radius logs, such as the call station ID, the calling station ID, anonymized of course, and performance information, download throughput, local ping, and upload throughput. Apart from the Kibana user interface, let me show you how this information is visualized in the WiFiMon user interface, which includes these tabs. The most important tabs of the WiFiMon UI are subnets, which corresponds to crowdsourced measurements, and the hardware probes that correspond to deterministic measurements. In subnets, this is crowdsourced measurements. You can see our last measurement here. An important thing to notice here is that the client IP is also stored anonymized in the Elasticsearch cluster and depicted anonymized. Next, you can see that we also include correlated information such as the average download throughput per access point MAC address here. Let me show you also what is depicted for hardware probes. Earlier, I have included measurements for 3 hardware probes. You can see them here. They are differentiated based on the test tool that is used. You can see that we append the number of the hardware probe. For example, this is hardware probe 1, hardware probe 2, hardware probe 3. Finally, let me show you what information is depicted in how information is received from the hardware probes, such as the wireless network metrics and surrounding information, such as the nearby SSIDs, their MAC addresses, and their signal level link quality. I will execute this script. This is a script included in the cron tab of the hardware probes, and see what I will get here. As you can see, I get the timestamp of the measurement, the access point to which the hardware probe is connected, bitrate, link quality, the MAC address of the hardware probe, as well as signal level, transmission power, and information about surrounding ESSIDs. Here you can see that this is the name of the ESSID and the MAC address, and this is the link quality and signal level. I hope you enjoyed the demo of WiFiMon. Thank you.
Okay, thank you, Nikos. Thank you for this video. I will now just return back to one slide. So you've seen now how WiFiMon operates, and you've seen what are the key components of the system. So I can if I would like to summarize it, I could tell that this is not a system that was developed from scratch, and there is not too much development inside, but it is more a system that uses different other well-known tools like those Speedtest and Akamai Boomerang tools for verifying HTTP performance and network performance on one side, and on the other side, Elk Stack and similar software that is being used to stream and store all the data. Having said that, I would like just to return to explain the service model that we prefer and that we offer with the WiFiMon. So as Kurt said at the beginning, there are two delivery options. The first one is that you download and install all the components, that you install everything based on the manual that we prepared and that is on our wiki page. And of course, you could get the support from the WiFiMon team. This means that we can guide you through the installation process and give you all the support in that sense. But all the components remain installed in your institution and all the data remains there. And this is, as it is written here, the preferred WiFiMon service model, because especially because of the data, because when you monitor Wi-Fi networks, you can store there some information like the MAC addresses and IP addresses, even though they are pseudonymized and they are hidden from someone who is operating the system. It can still reveal the data about and it can lead to the person that used the device at that moment. So in order to avoid any sort of transfer of this personal or personally identifiable information towards the third parties, we prefer this this service model. On the other side, if you would like to try it and you don't want to use it in a production environment, but would like to try the system and how it operates, we can offer you the installation of the most complex component, and this is the analysis server. This is the Elk Stack component. We are offering this to be installed and used from the NMAS system. That is the system that is also being operated by our task. So this is actually a Docker container of the WiFiMon analysis server component, and you can by several clicks in, let's say, 10 to 15 minutes, get the operational WiFiMon analysis server. What is left for someone in that case is to install the test server and any number of hardware probes. So I wanted just to explain this, and I think that now, after the whole explanation of all the components and what is inside this, this gives and a bit more light on the way WiFiMon is being offered, and in that. And now, if you would like to learn more about this, and if you would like to find the documentation and installation instructions and so on, you can go to our wiki page. You can also find the WiFiMon code that is gluing all these components. Yeah, maybe now I can stop sharing. Of course, we can return to any of the presentations or slides if you would like to. I've heard that there are some comments in the chat, but I was not able to see them during this presentation. So if we can now, please, I ask all the participants of this InfoShare to ask the questions. Okay, so I don't know. Maybe if Tim and Ivana can help me with the order of these questions, so that you don't wait for me to browse through the chat history here.
So the first one that I see is from Anders Nilsson: collecting MCS and retry rates, would that much info? And Nikos has provided some reply, but Anders, if you want to ask the question, and then the team can try to address it.
Do you want me to unmute myself, or?
That would be useful.
Yeah. Okay. Well, I mean, the key thing here is when we're looking at things like throughput, we don't know the actual reason why we're getting this or that throughput. Is it due to the fact that, I mean, to start with, we really need to correlate this with the amount of users we have on the actual cell, and also the kind of quality we have one thing we don't get info here about is the fact that it's very typical that some clients are so-called sticky clients and of course are connected to the Wi-Fi, but not necessarily the best access point. And that the result of that usually is that you get poor performance. And one thing you can use to notice that is either you have, well, you do collect the signal strength, so that's one way to catch it. Another way would be to see that you have a lot of either retries or that you have a low data rate because it rate shifted down to a lower MCS. When I'm talking about MCS rates, I'm talking about data rates usually. So that's the point I was trying to make.
Thank you, Anders. Any comment from the WiFiMon team about this? Okay, the next question was from Ivan. He said, how come crowdsourced results reach higher throughput than the test probes? So this is easy. Even I can answer this one. I don't know if you remember at the symposium or at the TNC 19, if you saw us there, we've been forced to put the hardware probes near to the power plugs. So hardware probes were not in the good places. If you look at the distance from the access point and so on. So the hardware probes were somewhere on the floor, maybe behind some closet or something like that. So this is why some person who was sitting in a chair probably close to the access point was able to get the better throughput than the hardware probe. But I think that you should not look at the absolute numbers. With Wi-Fi monitoring, I think that the relative change is something that you should observe rather. Because, for example, in all these results, you can see, and what we observed is that for example, the signal strength was quite good and it was stable throughout during the whole period when we observed it. But on the other side, the throughput was varying, and this is because of the impact of the other users, of the stress on the Wi-Fi network, and so on. So I don't think that we should be very much concerned about the absolute numbers. What this throughput means is really difficult to measure, because it's not something that you can compare with the achievable throughput that you can get on layer 2 network, wired network, where it is relatively deterministic. But even there, it is difficult to estimate. And here, this is the HTTP throughput. So there is also an impact of the load on the web server, of the network, on the link between, and also, as Nikos said, one of the important thing is the placement of the test server, because this is the TCP throughput and not the UDP throughput. So with TCP throughput, there is a significant impact of the round trip time between the two machines, because of and also there is a trade-off, and there is a page in the wiki which is describing this in our WiFiMon wiki. There is a trade-off. If you would like to get the more accurate throughput test, then you would need a larger file, because you want TCP session and those windows to increase to the maximum side. And on the other side, if you want to not to create too much network overhead on monitoring, then you want to keep those images that you are transferring rather small. So if they are small, then the window doesn't get to the maximum size, and what you are measuring is something that is a throughput of the TCP session that is increasing the throughput. So this is why, as I said, don't look at the absolute numbers. That this definitely doesn't make sense. This network and the performance of the network and the throughput of the network is not measured in kilobytes per second, but look at the relative difference between the measurements.
Lovely. I'm not looking at the absolute numbers. You know, even in my question, I'm comparing the results from the two sources. So I'm comparing, and I see the answer from Nielsen is it makes some good sense. but still, do you have then kind of, my take from here is, from this answer, is that the probes were not positioned well enough, and yeah, so it's not kind of a denting case. But do you have other results? I mean, something from something else?
We have a lot of results, but I think that we would need about an hour to present all the results of all the measurements from all the hardware probes, and we have also the locations where they were, and we would have to describe the.
So you had a better event that you could show here, not
not a better event, but we this is just. We wanted just to give you an idea what you can get, and this is not I would say a thorough investigation of what happened and why. I mean, we can explain this, but as I said, this could be a separate presentation, how to understand the results that you get from the WiFiMon. And in that case, you would have to also take a look at the layout of the hotel in Ljubljana and so on, and the locations of the access points and the hardware probes and so on. And this is we don't want to go into. I mean, we can,
yes, okay.
if there is a need, we can go into.
Of course.
If I just can make a comment. I mean, the results that you have seen from two events where we actually wanted to do the proof of concept, to actually see how this could be measured, what should be done, what can we actually see out of this. If we are considering implementing WiFiMon in some local area network that is under our control. So if we are managing a Wi-Fi network and want to use WiFiMon to monitor this, in that case, you can probably have much more freedom in where will you place the probes, how will you design the actual monitoring network. You might also be in position to track the measurements through time, and then to see if there is some better positioning or different tuning for this. So on a longer run, it might might provide much better and finer tuned results than from the two pods that we set up just for some event in a relatively short time.
So then, are you then considering some sort of kind of, or do you have a pilot NREN, or where these things are being kind of optimized? Because I would also, I cannot, one can easily see that even the probes that are set up there, you will see that the results, even during these times that are not peak times, when people moved from one location to the other, they are still not that stable, I would say. They have quite much of a deviation even there. I mean, it's almost 1,000 units of, I guess that's 1 megabit, right? I'm not sure, is it in kilobits or in megabits? But anyway, the deviation there in between these crucial points is still high, and perhaps the explanation that the probes were not in the best location is good, I would say. Still, do you have something, or is it the Raspberry Pi that needs to be a different device? I'm not sure.
I think we could consider those points, and certainly there's the option to use different models of Pi with different hardware and so on. We've got a lot of other questions though.
Yes,
and time is ticking fast, and we can. Very happy to follow up offline with you. Stefan asked to have two questions. So Stefan, if you want to, the Stefan, sorry, I didn't realize. You're going to ask an EduRoam question, presumably, but go ahead. You're breaking up a bit, Stefan, sorry. You might need WiFiMon.
Let me see if I can tune this a bit.
That's better.
Yeah, that's better.
Okay. So actually, I think the solution is actually very impressive.
No, it's gone again.
Okay.
Turn off the video or something. Okay, so while Stefan reconnects, what was the next question? It was from Harold about scaling up, what the largest tests we've done and how we might go about supporting much larger tests. Do you want to ask the question, Harold, or is that enough for you? I'm not seeing, oh, there we go. Oh, I'm not seeing Harold demute. So does one of the team want to ask her the question? What about scaling up to 1,000 APs and 5,000 clients? Is there experience with an environment of this size? Well, I think the answer is no as yet, but does anyone on the team want to answer the question? Or make any comment about larger scale?
I think I can answer. Unfortunately, we don't have such an experience, but we're currently working on scaling the WiFiMon analysis server in multi-node ELK cluster. Probably this will provide better results. This would mean that we will have multiple nodes with Elasticsearch, and the visualization will come from one point in the WiFiMon analysis server. And it is on our future directions.
Okay. Do you want to try again, Stefan?
Okay.
That sounds better.
So first, it's not an endurance question. So I think you have a solution here which works perfectly across Wi-Fi networks. So first of all, that is quite impressive. I really like the presentation.
You are breaking up again, Stefan. Sorry, it was fine when you first started speaking. I don't know.
Can you maybe try without the headphones?
Let me switch to it.
Just write it in the chat, Stefan.
Yes.
Okay, so can you hear me now?
Yes.
Does that work any better?
Oh, yes.
Ah, okay. Different microphone. So yeah, so first impressive work. I really like the WiFiMon for being useful generally on Wi-Fi, independently of if it's accurate or not. But my question is actually a different one. So when you run your measurements, do you download with the full available speed? Because if you do, you're competing with the bandwidth for other people, so you're a bit contributing to the problem if there is some. Would it be possible to have a speed limit for the tests and say, if I make my downloads with 1 megabit per second, I'm happy, and then I leave it at that, so I'm not disturbing the rest of the world?
Okay, who wants to take that question?
We don't have something that, if I can understand correctly, you mean that if the performance is not good, to abandon the test?
No, not quite.
I think Stefan's point is that the test itself may be slightly disruptive on the network, but I think for each client, it is performing one download of up to, well, it depends what file size you put that up to, maybe 5 meg file. And the argument is that the download is representative of a typical full web page download. And the test can also be rate limited by the cookie principles. So
the data transmitted are few. They're not that disruptive. The tools do not consume a lot of bandwidth, and we also have the optimization of the cookie that Tim mentioned, which does not allow a user to perform multiple tests.
The interesting
so I think
question for you, Nikos, is whether the tools that are used like NetTest and Boomerang and whether they support a maximum download rate in any way. Is that possible? If the site wanted to configure that, is that possible?
No, I'm not sorry. I'm not very sure. I will have to check, but the tools are not disruptive.
Okay. And
I would guess this can happen on the test server, where you could say limit that session to this amount, and then so to not allow that throughput.
Yes, to specify the data transmitted by the test tools. Yes, this is configurable by the test tool. For example, Libretest can configure the maximum amount of data that will be
for each session.
Speedtest has a lot of parameters, and they have a very detailed guide that says how to configure them. You can use the default parameters or configure other values and impact the accuracy. Okay, sorry, I didn't understand the question first. I hope this covered.
That's a great answer. Yeah. So my second question is, less sophisticated. I'm just wondering. So if you specify a big subnet, let's say a generous /16, so you want to monitor your network, you would probably also run the tests on a wired subnet. Is WiFiMon prepared to receive such measurements? Will it break if you try to do that on a wired network?
From a /16. This depends on the number of the tests performed per minute. I don't think it is a matter of how big the subnet is. You're muted.
Okay, I only heard the last 2 seconds of what you said. Could you maybe repeat?
I also have some trouble hearing from you. I think the size of the subnet is not a big deal. It is always a matter of how many devices there are in the. Sorry, how many measurements are performed per minute.
Yeah, okay, but I could run the JavaScript measurements on a wired subnet, and there would be some results, and WiFiMon would be able to make sense of them. Is that right?
Yes, you could also use it for wired networks, but this is not the purpose of WiFiMon. And if you're asking me how do I differentiate between wired and wireless network, this is by using the subnet tab, in which you configure the subnet that's going to be monitored. The wired, the idea of WiFiMon is to compare crowdsourced and deterministic measurements, not to compare wired measurements.
Yeah. So maybe I should suggest say what my use case is. I've just spun it around in my head. So we are an NREN, and we would like to monitor all the Wi-Fi networks we deploy, let's say with Ethereum, but not for all of those networks we have the exact subnet sizes centrally managed, because this is being done by schools and whoever. So what we would have is a web page that everybody goes to fairly regularly, and we can put up a server which does the measurements. But when it comes to the subnets, we can't only list the Wi-Fi subnets. We would have one big subnet, which is our NREN backbone, and then we would have lots of results coming in, many of those pertaining to Wi-Fi networks, but just as many of those coming from the crowdsourced measurements being executed as it happens on a wired network. So if that mix of measurements comes in, can you make sense of that in WiFiMon?
You could maybe differentiate using the IP address. I'm not sorry, I'm not very sure to respond to that question.
Hi, I'm sorry, Nikos.
Yes.
Let me give you an example of a real case. In FCCN in Portugal, we share the same network, the same IP address network for Wi-Fi in EduROM and for the stations that we are working. Can you differentiate the traffic coming from my laptop via a cable or via Wi-Fi, for instance? We share the same network. It's the same /24 for our institution. I think this is what Stefan is saying.
I'm not sure. Probably you would receive and process both measurements, but if you use correlation with radius logs, you could be able to differentiate between them. Probably with correlation with radius logs. Unfortunately, you would probably process all the information.
Yes, so I guess they don't mind, mind having data from the others. The question is, I would put it in another way, perhaps, and I'm not sure if the guys can confirm, is if you can graph it, present it for the wired devices and for the Wi-Fi devices, differently. Because if I understand it also correctly, you are able to capture which device had some strength signal and all the parameters that are coming from the Wi-Fi device, right?
Yes, wireless metrics are included.
Yeah, so that means you can differentiate between the wired devices and the wireless devices. The question is then, can you graph it as well, differently?
I'm sorry, there's another problem, because as you can see, if I am having a problem with my Wi-Fi, but not in my network cable, the data of the throughput that I get from my laptop poisons the data received for the Wi-Fi. So it's not comparable. So you have good data from the cable and a bad data from the Wi-Fi. So if you are using this information, you are poisoning your data.
Then maybe this is a future direction, maybe for WiFiMon.
We are just showing you some possible problems or some situations, not trying to do anything else.
Okay. It'd be good to follow up with you and just discuss that further. I think one thing to note is the subnets that you can configure. Those are essentially determining where the tests can run from. If you've got additional wired systems in a subnet that might have wireless as well, then the only way you can determine that post-test is by either the correlation that Nikos mentioned or maybe some observations of the plots. Shall we move on to the next question? What have we got? Peter has asked, how does WiFiMon compare to commercial products like 7Signal, Mobileye, Plume, or Cinefa, or NetBees, as Glenn has added? Any comments on comparison to commercial products, Nikos, or anyone else from the team? Kurt?
Yes, so if what is the basis? What is the base of WiFiMon? WiFiMon is set up on crowdsourced based measurements, right? So not the single point of measurement is important, the mass of measurement is important. I don't know Plum and Cinefa in detail, but I think it's not comparable with traditional commercial products. As I said, the crowdsourcing is the approach that is staying behind, and we measure a mass. We have at the end a mass of measurement, and what we like to have and what we like to see is the throughput and latency and the all other metrics, so that we get in a time series analysis over a time period, an accurate statement. What is the Wi-Fi performance on the campus, right? So it's not the single point. It's not the deterministic measurement that we are looking for. Is the opportunistic, the crowdsourced over a time. So also what you see by our statements of performance measurement in the presentation is we were there, and as Ivana said, there is someone, they comes to us and say, could you measure the Wi-Fi performance? And we said, okay, we'll try, we do the best, but this is a spot we measured there for 3, 4, 6 hours, right? But what the use case of WiFiMon is to measure over a longer period and to make time series analysis, and then you can have, and then you get a statement, how good is your working, how good is your network working, and is your setup optimal or should be reviewed, right?
Yeah, I think, I mean, I looked at the NetBees tool which was mentioned, and NetBees tool is something very, very similar to our hardware probe. And this is basically something that the metrics that they are getting from those probes are very similar or the same, I would say, from what we can provide with the simple Raspberry Pi. The difference is that this is open source and this is free. This is a big difference. And the other one is that we also, as Kurt mentioned, are adding this crowdsourced approach, and you can get the impression of what user actually gets. I would like just to return a little bit to the previous question. I still don't know why in your local network you don't have under control which IP addresses are getting wired and which wireless devices. I mean, you can do that from the DHCP or whatever you want. And in that case, if you know which IP addresses are going to be obtained by wireless device, then you can definitely restrict the WiFiMon to receive the measurements from these devices. So this is something that that I think that still you can have under control if you would like.
Yes, we can have it under control, but it's the deployment that is made. I do not control it. I manage the EduROM hotspot, and I am looking it at an EduROM perspective. And also, we tend to see this in many institutions, Portuguese institutions. The same pool for the DHCP is used both in Wi-Fi and the wireless networks. So it's
yeah, it's difficult because these measurements are on layer 3. This is HTTP, and in that case you can't tell. But if you do a little more effort to distinguish between the wireless and wireless devices, then you can make this distinction.
I think the way it's do a correlation with the not with the DHCP and the radius logs. So if you don't, if your MAC address or your IP address is not registered coming from the radius log, so let's put this data aside or put it in another shell with another information.
Yeah, that should be possible, but the masks themselves can only control what nodes can run tests. But
actually, in our case, it's the odd number is for the wireless and the even number is for the Wi-Fi. So, but it's our implementation.
Interesting. Okay.
So it's just another case that you might stumble upon.
Yeah, and
oh, sorry.
If you know that it's even and odd, then you can definitely have it under control. Yes, good point. Good point from Indrek, and thank you, Indrek, for this. Indrek was a member of this team in the previous project. WiFiMon doesn't require user to download anything special. There is no client application, which I saw that some of the commercial solutions proposed. So with the WiFiMon, if you use crowdsourced monitoring, you just visit a page, which can be, if this is a campus network, maybe a popular page for students that they visit very often. I don't know if they have to do some administrative stuff at university or something like that. So they don't have to download and install anything. They just visit the page and it happens. This magic happens. It's a couple of megabytes that they download, and this is how you obtain the measurements from various different devices. Okay, yeah, an agent can provide more data, but can you be sure that if you have students that they will like to install the application and click on it every time or every now and then? So yeah, it's difficult. It's true. If you allow this application to access some of the Wi-Fi interface data, then really you can get more information. But I don't know. I think it is important that you don't bother users too much and to ask them.
Everyone who volunteers to install it is included in getting a prize drawn.
Yeah.
They get a free week in somewhere. Yeah. When and if we can travel somewhere.
Well, that would be nice. we don't have this in WiFiMon service offering. We don't have this option. So. Okay, it's 14:29 according to my clock, so it's 1 minute till the end of this session.
Let me just let you give me just one last question.
Yes,
Ian, I'm
please.
sorry, I didn't enter at the beginning. Probably I'm just repeating something, but can I have several pages for the tests affected to one subnet? Let's say Lisbon is in the subnet X, goes to page lisbon.fccnpt. Porto is on the subnet B, so it goes to Porto dot something. Can I have?
Yes, definitely you can have it, and you should have it, because if you would like to have a single test server for the whole NREN, that would not work well, because if for example the test server is in Lisboa, then the measurements over there would look much better than the measurements from Porto towards Lisboa.
Okay, it's also makes it scalable for the universities, because if you are in a university, on university A, you should be in the nearest point, in the nearest test point. So it's more scalable for a nationwide. Once again, in your own perspective, it's better for a nationwide deployment of the WiFiMon.
Yes,
exactly. It was also at the beginning of the WiFiMon project. It was the essential question that I mentioned in the slides or in the audio, that we are collecting data from distributed sources. It's very important that you do that.
And also probably do in case of a problems of an endpoint, you may probably redirect it to the nearest endpoint that it's available for the tests. Okay.
Yes.
Okay, thank you.
Okay, so thank you all for being at this WiFiMon InfoShare. I hope it was informative and interesting for you. As I said, please take a look at the slides and take a look at those links that we have over there. Subscribe. I saw already that we had some subscriptions to our WiFiMon mailing list, so please do that if you're interested to hear and to be in contact with us and to get more information about the WiFiMon and the news, because as you saw also, we have some new features that will be installed very soon and implemented in WiFiMon. So thank you all again for being at this InfoShare. Have a good day, and I hope to see you soon again. Bye.
Bye-bye.
Thank you all.